Okay, following on from our previous video on connected particles, we're looking at pulleys. Now, pulleys in year 12 is very similar to connected particles, except it kind of just takes it and bends it round a corner. So pulleys are always described as smooth, which means that we can assume the tension either side of the pulley in the string is the same. So that'll always be the case, and in fact that's always the case of second year as well. And it essentially takes the tension force and bends it round a corner. So we've got a tension force acting that way, a tensing force acting that way, and it goes around some kind of pulley like so. And then you just apply F equals ma to whatever is going on. I mean, your tension force will be pulling on the objects as opposed to pulling on the pulleys with the same T, so all the same T, and just apply F equals ma. The acceleration of the system will be the same across the two objects, because as this one moves, that one moves. Again, the string is described as inextensible. So they're very similar to the connected particles, except it just goes around a corner. So let's have a look at some of these in action then. So here I've got part of a table, and there's a 20 kilogram mass on the table, and there's a 44 Newton resistance to that mass, and then I've got this 5 kilogram mass hanging over a pulley. Okay. So my question is, well, is this system moving? All right, let's just have a look. What we can do is we can calculate the acceleration is going to be acting downwards if it's going to move, which means the same acceleration is going to be acting to the right on the top. We're going to have this unknown tension force acting upwards there, and unknown tension force acting to the right. On the pulley itself, it'll be pulling that way and that way, but we don't really need to label those at all. Vertically downwards, we're going to have the weight of this, which is going to be 5g, or 5 times 9.8. That's not 5 grams, that is 49 newtons. And then we also will have, we've got the resistance force over there. There will be a weight acting here, but it will just cancel with the reaction force there, so we don't really care. And we can assume that this table is horizontal, and if this were an exam, they would explicitly state that. So applying F equals ma to this mass and to this mass. So I'm going to resolve vertically for the first mass, and I'm taking downwards as positive because I'm labelled my acceleration as down. So I've got 49, which is the force downwards, minus my unknown tension. That's going to equal the mass, which is 5 times my unknown acceleration. And if I do something similar with the 20 kilogram mass, but this time resolving to the right, again taken to the right because my acceleration is labelled to the right, I've got a tension to the right minus a 44 to the left, and that's going to equal the mass of the object, which is 20 times the acceleration. Okay, and what we've got there is a pair of linear simultaneous equations. Now what's nice about this is when you add these two equations together, the tensions will cancel, and that will always happen. And then we've got 49 minus 44 is 5, and that's going to equal 5a plus 20a, which is 25a. So that tells us that the acceleration is a fifth, or 0.2 meters per second squared. And if we pop that back into one of these, we can get that the tension is 49 minus 1, 48. Okay, so that is, that's our values of A and T. Example number 2. The figure to the right shows two masses connected by a light string which passes over a smooth pulley. Again, we can see that word smooth coming up. Initially, the blocks are held at rest, but they are then released. Find the acceleration of the blocks and the tension in the string as the blocks begin to move. So we're not told which direction these blocks are going to move, so you could intuitively work out that it's going to be the 5 kilogram that's going to be pulling down and the 3 kilograms is going to be going up. But if you get it wrong, it doesn't matter. Your A value will just come out to be negative. So I'm going to label this as A. That'll be going down. And I'm going to label that as A going up. And the reason why they're in different directions is because of the pulley is changing the direction of the tension. So the tension is pulling this one up, and it's pulling that one down by its weight. So that's 49 downwards. Downwards on this one, we've got 3 times 9.8, which is 29.4. Yeah, sorry, mind blank. And then a tension pulling that one up. And that'll be the same tension force, and that is because the pulley is described as smooth. And also, the string is light. So that also allows us to assume the tension is the same across the string. Okay, so now we just apply F equals ma to both of those. So resolving vertically upwards on the left-hand one, because up is positive, I'm going to have T minus 29.4. That's going to equal the mass times acceleration. And then resolving vertically, but downwards this time on the right-hand one again, because A is listed as downwards. So that's 49 minus T is going to equal 5 times acceleration. And again, I've got a pair of simultaneous equations. Just like in my previous example, if I add these two together, then the T's will cancel. So this time I've got 49 minus 29.4 is 19.6. And that equals 8a, which allows me to state what a is. So I'll get 19.6 divided by 8, which is 2.45. And that is meters per second squared. And then that allows me to state what tension is. Again, by just popping it back into one of these two equations. So 3 times 2.45, the top one, plus 29.4. Gives me the tension is 36.75 newtons, and it is always worth checking your answer where possible. So pop it into the bottom one. 49 minus 5 times 2.45 should give me the same answer, which it does. So that confirms that they are both correct. And third and final example, example number 3. The figure above shows a 6 kilogram block on a smooth horizontal table. It's connected to 2 blocks of mass 2 kilograms and 9 kilograms by 2 light strings which pass over smooth pulleys at the edges of the table. The string attached to the 6 kilogram block are horizontal. So this part and this part, they're both horizontal. And as it goes over the pulley, we can assume it's vertical as well. And that's because there's no horizontal forces acting on these blocks. So you've got its weight, which will cancel with the tension. What information in the question allows you to assume there's no friction between the block and the table? Well, the fact that we've got a smooth table. So the smooth table allows us to assume there's no friction. The tension in the string is equal either side of the pulleys. Okay, so how can we assume that the tension here is equal to the tension here? And that is because we've got smooth pulleys. And what in the question allows us to assume the mass of the string is negligible, and it is that it is light. So a light string. So for little 1 markers, you might get asked about modelling assumptions. Now onto the kind of bulk of the question. Calculate the acceleration of the system and the force in each string. Okay, so we've got 3 unknowns, so we need to get 3 equations out of this system. So we can see that this is 2 kilograms and this is 9 kilograms, so similar to my, I think it was my second example, wasn't it? Yep. If the system is going to move, we can assume it's going to move this way round, so that's 9 is going to go down and the 2 is going to go up, which means the 6 is going to move to the right. So label it up. Acceleration downwards. Acceleration to the right, acceleration upwards, because the pulleys are moving it around. So my positive direction isn't a straight line anymore. The positive direction kind of goes around the system. Label the tensions. So we're going to have a T1 over there, and then we've got a 19.6 as a weight. Because the pulley is smooth and the string is light, that will also then be T1. This is a different string, so a different tension, T2. Again, the pulley is smooth and the string is light, so that will also be T2. And then we have 9 times 9.8, which is 88.2. There will also be a weight and reaction on the 6 kilogram block, but just like in example 1, they bear no bearing on the question, so we can ignore those. Okay, so just applying F equals ma to each of these parts of the system. So let's resolve vertically downwards. At the right hand weight, we're going to have 88.2 minus T2 is equal to the mass times acceleration. Resolving to the right of the 6 kilogram mass, we're going to have T2 minus T1 is going to be equal to 6a. And then resolving vertically upwards at the left hand mass, we're going to have T1 minus 19.6, and that's going to equal 2a. It looks fairly complicated because there's 3 equations there, but in exactly the same manner as we had in the previous 2 examples, if you add those equations together, the tensions will cancel. So the T2s will cancel here, the T1s will cancel here, and you're left with a number on the left-hand side, which is 88.2 minus 19.6, which is 68.6. And that's going to equal the sum of those, which is 17a. So if you divide both sides by 17, we will get the acceleration. Some hideous number. But we get that the acceleration of the system is 343/85ths, which perhaps as mechanics we should approximate to 3 sig fig or 4 sig fig, 4.035, and that'll be meters per second squared. It's also asking for the force in each string, so now we can use that definition of A in this equation to get T2 and this equation to get T1. So let's just store that in my calculator memory as A, so that's now stored in there. T2 is 88.2 subtract 9 times A, which is 882 seventeenths. So T2 is 882 seventeenths, and that is approximately 51.88 newtons. And we can do something similar for T1. Going to go back up to here. T1 is going to be 2a plus 19.6, and that gives us 2,352 85ths. 2,352 85ths, and that is approximately 27.67 newtons. And we should perhaps check those numbers with the 6 kilogram block, or the middle equation if you like, just to make sure that they are indeed correct. So if I do T2, which was my 882 over 17, minus T1, which was 2,352 over 85, that should equal 6 times the acceleration. So therefore, if I subtract 6 times the acceleration from that, I should get 0. So if this is 0, then I can be fairly confident that all 3 of my answers are correct. And it is 0. Perfect. So that gives me a nice nice confidence that I am correct. Okay, and that's pulleys. That finishes up the forces chapter. It's just variable acceleration left to go. Thank you for watching.